Okay, great. Let's get started. I'm James. I'm a data scientist here, and I worked on a project of how we can detect AI-generated text. This was our goal, and for extra motivation, I shamelessly stole this from someone else, so I was extra motivated to do this well. Now, before we can discuss how we can actually detect AI-generated text, I'm going to continue from where Mike left off and discuss how models generate text. He's shown how we train these models, but he hasn't actually shown the process by which a text is created. So let's get started. Everyone's used an LLM at some point, and you put in a text. Oh, hello. So you put in a text, and hopefully something happens, and the output you get is in some way related to what you put in. Not always, but generally. But what actually happens behind the scenes when this occurs? So largely speaking, an LLM can be split into four main components. First, you have the tokenizer, and this just creates model IDs, token IDs for words, right? So for example, me and I, while being two similar words, might have completely different IDs. Then, as Mike pointed out, first an example, so we can see, by the way, all the code that's presented here is also going to be published as as a Python notebook, as a Jupyter notebook that we will share with you, and you can mess around with all of this. Yes. Great. So the tokenizer, as we said, is just IDs, and not every word necessarily has an ID. So for example, if you look up top, then cat face, unsurprisingly, isn't a single token. It's split into two. And a token isn't necessarily a word either. You can have punctuation. So for example, if you have the word wide, then Y and apostrophe D are split into two separate tokens. This is just an introduction into how the tokenizer works. But as I pointed out, this is ultimately arbitrary. This depends on what data set you trained it on. For example, as he mentioned over there, then you can use NLTK to create your tokenizers too. Now, the next part, which Mike also discussed, is the embeddings. So you have the embedding layer, and this essentially contains all the contextual information. It's a vector. So when you look here, this is just an example embedding in 3 dimensions. And of course, usually embeddings are somewhere between 1,000 if you're DeepSeek or 4,000 if you're anybody else, essentially. Then here, context becomes very apparent. For example, me and I have vector representations that are very close together, whereas arbitrary is far away from them, regardless of their IDs. Another aside to connect to what Mike said, it's this embedding similarity is what's used in RAG as well. Now, the next component that we have is computing the logits. So we wanted to be able to compute the probability of what the next word is, because at its core, an LLM is a next word probability model. That's all it is. So what you'll get is for any input text, you'll get unnormalized probabilities for every word within a lexicon. And to help demonstrate this, I'm going to use an example. So I'm going to use the lyrical tapings and timeless music of one Avril Lavigne. So taking the sentence, why do you have to go and make things so? Now, to those unfamiliar with her music, 1, you're missing out. 2, trust me, the next word is complicated. Now, we can put this into an LLM. And again, I'm using the Hugging Face library here. And we can see that for every token in here, you have probability output. And this dimension that's your vocabulary. That's your bag of words as it was once known. And it represents how many words the model knows, or how many tokens, rather, the model knows. And it predicts an individual probability for each one. And you can see the logits here. Now, the logits obviously don't help us, and we have to normalize them. Typically speaking, how do you normalize logits? You use a softmax function. This isn't something unique specifically to LLMs, but it's used here too. However, in LLMs, you have one extra parameter, which is the temperature. The temperature, the higher it is, the less the probability itself matters. Take the temperature to infinity, and then essentially every word is equally likely to be next. And we can demonstrate this using our previous example. So we can print the probabilities of the top 5 most likely words, and lo and behold, GPT-2 knows the song, as well it should. As well you should as well if you didn't know it. But there is one more step that happens. We don't actually look at the probabilities of all the words. This is something the models used to do, where it would look at the probabilities of all the words and then select one. But what we found is that the generation of the text was very randomic and sparse. So, and I'll demonstrate why this happens in a moment, but here's the solution. You can use either a top P or a top K approach. And chances are, if you've ever used an API for be it OpenAI or Google, then you've seen these parameters. Now, what they do essentially, I'll start with top K, It says only look at the k most likely words. Select from them using the probability distribution. Top P says that take the top probability mass. So for example, if I selected 0.3, then take as many words until the probability mass reaches whatever you decided and select from them. And why is this necessary? Because let's take another example where my initial sentence is don't. So previously, I looked at the top 5 probabilities. Here, I'm simply going to ask how much probability mass is outside the top 5. And we can see that the vast majority of the probability lies beyond, meaning that if you didn't filter down to some top K or top P, you would create very chaotic output because you have such a huge vocabulary that the probability mass is still dominant outside the top most likely selections. And what does an LLM do? It repeats this process every single time it adds the next token it generated, and then feeds it forward back again until it reaches the end of text token. Why is it such a unique, funky looking thing? It's because during training, we also use this, and you don't want to use an end of text token, which might occur naturally somewhere in the text. Note that the tokenizer itself is model specific. You'll also see this in the notebook. The examples I'm using are from GPT-2. I purposefully picked a very lightweight model that anyone can run on pretty much anything from a potato to your phone. But you can also change this. You can experiment with DeepSeek, for example. I don't know if they're on Hugging Face yet, but I imagine they will be eventually. Thank you. Now, we've discussed how an LLM generates text, and in a moment, we'll discuss how we can use this to calculate features to predict the text. But before that, I want to also discuss on what behaviors will manifest themselves when LLM works the way it does. And to do that, we need data, because we need some live examples. Now, we know that whenever you train any model of any kind, the data you pick, what you train it on, is what it'll be good at. And what we want to do at the moment is we want to look at news style content. This is purely for the demonstration purposes. We train this on a much larger data set. But how we will create our data set? We will take a headline from an article that exists somewhere. Also, if this seems excessively harsh, it's because I wrote it. And we will ask a model to create a headline with this given title. And that will be our real and our AI-generated text. And we'll create a whole bunch of them, and OpenAI will be happy because we paid them way too much for it. And that's the data that we will demonstrate on. So what can we do with all of these for features? Tokenizer, as I mentioned, it's arbitrary, and worse still, it's model specific. We want to be able to generalize. So this isn't something we can inherently use. Now, the embeddings, on the other hand, they contain all the contextual information. However, unlike most vectors, because as the data scientist, you see a vector, first thing you want to do is calculate all kinds of statistics on it. But the problem is with an embedding vector, it's not something that's orthonormal or in any other way intuitive. It's something that was trained and is essentially black boxy. So we will take it as is, and the fact that it has large dimensionality is something we will deal with further down the line. Now, the logits, they can serve us, we can use a pre-trained network, hopefully something lightweight like GPT-2, and we can generate a probability for every single word in a given text. And to demonstrate this, I go back to Avril, but with a different song. So we can take a text as is, and we can run it through the model. And as you can see, we can generate a probability for every single word in this text, or token rather. But in this case, I purposely picked something that maps word for token. Notice, by the way, that the first word doesn't appear here. This is because, unlike something like stable diffusion, where the input can be random noise, you have to start from somewhere. You need a starting point. You'll also see here that you have to move out the first token and the first label. Well, sorry, you move out the last label, the last logit, because this is a prediction for the next word. This is something that you will also see in the code. If you look at the loss function from most LLMs on Hugging Face, you will see this exact thing. And so we can use the logits, as I mentioned, to create a vector of the probabilities. And this, again, is a large-scale dimensional vector. But this is something that is intuitive, and we can calculate probabilities on. The last thing that we can leverage is the selection process. So like I mentioned, top K, the default value for this that you will typically see is 40. And you can use this. You can ask yourself, OK, great, we have a text. How many of the words were in the top 40 most likely, for example? And this is something that very directly reflects upon the behavior of LLMs. And indeed, if you only use this one feature, you can already create something which is pretty decent. Now, that was the structure. But now let's see how they behave themselves. So something you'll see quite a lot, this is a typical demonstration, and was actually how we came up with the idea to do this project, is you'll take a human-generated text and an AI-generated text. The text chosen will also appear in the code, and again, you can change it out, you can see what happens. And what you do is you embed them every time adding the next word onto the text. Then you use PCA reduction to draw this in 2 dimensions. And you can create this funky looking animation, which I didn't bother with admittedly, which is, oh, okay, look, in the 2-dimensional embedding space, the AI text started here and it went all the way here. And you can see that towards the end, the jumps get smaller, whereas in the human text is more randomic and it moves around more. A really simple way to demonstrate this is a graph like this, which just looks at the ratios. It asks, okay, what is the distance ratio between the AI embedding space and the human embedding space? And you can see that this value gets really small towards the end because the AI text has to converge within the embedding space, as opposed to human writing, which follows no rules because, especially in 2025, people write pretty much how they please. At times, I'm not sure it's even English. But as I said, this is a typical demonstration. I don't personally like this. And indeed, when we tested out this approach, we saw that it does work, but nowhere near as well as something else you can do. So this is a generalization, right? Because you're only looking at the end. So let's look at the more general behavior rather than we can use. I also call the slide my excuse to put in some LaTeX into this thing. So if we look at the structure of an LLM and we write it out mathematically, you get this, right? It's simply a model that predicts the probability of the next word given all the text that stems before this. Now, I presume most people here who've seen something before like this ask themselves, great, how can I write this as a Markov chain? And there's been quite a lot of researchers who've asked themselves the same question. And the short answer is you can't. And the long answer is you mostly can't. And mostly is pretty much all I need, because like a true physicist, I'm going to use this symbol right here, which allows me to write whatever I want. Now, I'm going to say that in principle, there might exist some group of tokens that for any token, if it was the last one that appeared, then this thing will act more or less like a Markov chain. But I have no a priori way of knowing what the tokens are. This is why I need to generate data to demonstrate this next point. But logically speaking, what can this token be? Well, a language has structure, right? It's not just a random collection of words. So a good guess is going to be the end of a sentence or a new paragraph. So let's look if this actually holds water. So what we can do is we can make a probability density graph where we look at the probability of the first word within the 10th sentence. Why did I pick the 10th sentence? Because that's more or less in the middle of the text. I'm not biasing towards the start of the text. I'm not biasing towards the end of the text. And the red line is the AI probability, and the blue is human. We can see that these two things are incredibly similar. Now, logically speaking, what we expect from the structure of an LLM and how it works is that it starts somewhere and it can take a bunch of paths to get to the end, but it must converge eventually, right? There's a logical structure to a sentence. So to test this, let's look at how the probability of the last word looks here. And lo and behold, because otherwise I probably wouldn't be showing this, we can see that there is a significant difference that occurs between the human and the AI-generated text. So this helps to agree with the Markov chain assumption. And if this thing behaves like a Markov chain after specific tokens, that already opens up a whole world of feature engineering we can do. But here we only look at the start and the end of a sentence. This is also not the general behavior. The most extreme example, of course, is the probability of the last word. And I think this is a much stronger demonstration than the distance in embedding space, because we can see the last word, the AI has almost absolute certainty. By the time you reach the last word, you've generated a whole embedding vector. You don't have much where to go. You have to terminate. But again, this we only look at probabilities within sentences. But what happens within the sentence itself? Because that's also an element of structure, right? So we can presume that the probability of the next one is of the next token isn't just a factor of all the words before that, not only of the index of the word within a sentence, but also the sentence itself. How far into the text are we? And to demonstrate this point, we can look at the average probability within a given sentence. So let's look at the average probability of the first sentence. We can see that there is some difference between the AI, which is the red again, and the human-generated text. But it's not that significant. The difference, by the way, if you really break it down, occurs towards the end, unsurprisingly, like we showed in the last slide. But how does this look towards the end of the text? So when you look at the last sentence, well, the 20th sentence, because not every not every text has more than 20 sentences, you begin to see much more significant differences. What's more curious as well is that the human text hasn't actually shifted that significantly. This goes back to the chaotic nature of human writing. Okay, so now we've seen the behavior in terms of both the features themselves of the architecture, rather, of LLMs and the artifacts of what they generate. How do we combine all of this into models? Going back to this fantastic diagram. You know someone's proud of a diagram, by the way, when they use it in 3 separate slides. So you can use, as I mentioned, the tokenizer is utterly useless, so we can't use this for anything. The embeddings and the logits both generate large dimensional features, essentially the embeddings and the probability vector. Yes? אז נהדר. אני תמיד אוהב ששואלים שאלה שהתכוונתי לענות אליה במילא. אז כמו שאתה רואה, like you see, the probabilities can then also be used to calculate things such as statistics. You can also use a Fourier transform. You can do anything you want in them. The probabilities, unlike the embeddings, are a vector that has meaning. Every component is distinct in itself. You don't have mixing. So you can do pretty much anything you want to it. Moreover, like I mentioned earlier, you can look at how many of your words are in the top 40 in the selection process, etc. This is how we leverage both the architecture and the behavior I mentioned before. The behavior I mentioned before mostly comes through the probabilities and how you parameterize different behaviors. For example, the Markov chain-like behavior that we saw earlier. Now, how this model behaves, like how good can it be, right? That depends what features you use, because as I mentioned, you have large dimensional features and you have the smaller, more quality features. And almost intuitively, you could say that the large dimensional features you'll want to handle with something, say a DNN, and this will emphasize precision. In our testing, we saw that this had a very low false positive rate, but especially when you're dealing with something like embeddings, you are at risk of the engineered features, on the other hand, as I mentioned, they're far more quality features. So these you want to give to a different model. You don't want them to mix, because if you were to shove all of this and all of this into, say, a DNN, then you lose some information in the huge dimensionality of it. So these actually lend themselves really well to a ensemble architecture. And these, in our testing, both emphasize recall and, most importantly, generalizability. Now, how well can this reasonably perform, right? So in our testing, and I use a confusion matrix instead of F1 score because I needed to fill out a slide somehow, we can see that this looks great, this looks amazing, right? I was very surprised to the point where I was pretty sure I had a target leak when I saw this, but turns out I didn't. And for extra points, this actually generalizes well across LLM models. So we tested on, say, training only on ChatGPT or only on Vertex AI, and then we tested with different data sets, be it Llama, Mistral, Anthropic. I need to test out DeepSeek, let's see how well that works. And we saw that our F1 score doesn't decrease significantly at all across models. Like on the models that we trained on, we have an F1 score of, say, 0.997. When you train on different models, you still stay at around the 0.99 rate. This is generalized really well, especially the model that uses the engineered features. And this, again, is because we leverage the general behavior of LLMs. We didn't actually demand anything from any LLM specifically, but rather we leverage how they generate the texts. But you can equally say that, okay, great, but you were responsible for all the test data, so naturally you generate them in a similar way. How do you know that you don't have a very narrow lens that you're looking for? So we did a couple of things to test out this theory. The first is we simply looked for data sets from other researchers who tried the same thing, and we indeed saw that our model generalizes really well. There was Ghostbusters, if you've seen them, which I think 2 years ago tried to do something very similar, and we used their data set. It's a really quality data set for this kind of thing, if small, admittedly. But we wanted to see another way, because as I said, this was a small data set and it was built in a relatively similar way, and we want to branch out. So we decided, okay, let's set this thing loose on the internet. Let's just take every single page we can and try to classify it and see what shows up. So great, you get a web page, you get some text, and your model says it's AI generated. How will you actually know that it is AI generated? Now, of course, you can cross-validate with other tools because there are services that offer this kind of thing. But, worst case scenario, you're just wrong together, which is considerably better than being wrong alone, and indeed is close enough to being right if you're either a politician or a stockbroker. But on account of being neither, I wanted to validate in a more concise way. So what can I do? So the first thing I can do is to try and get rid of false positives. So instead of looking at individual pages, I can aggregate by an entity. Let's take a site. Let's take a specific author from a site, and let's look at the collection of their works through the lens of the model. This way I can mitigate individual cases of false positives or false negatives. And better still, this also gives me leverage to, well, I also set a minimum number of texts, of course, but this also gives me leverage to use my model, which has more generalizability and recall. It trades off lower precision, so it does have a false positive rate. By aggregating, this isn't as huge an issue. And this is the process we did. So now let's look at some specific examples, because at the end of the day, okay, great, you say that everything on this site is AI generated. But again, how do you know? So here are a few examples that we came across, and these are really blatant. So the first thing is AI can't count to very high numbers. What do I mean by that? A traditional problem with, before LLMs became a thing, people used LSTMs, if you're familiar. And they had an issue with context, right? The further away you get, the less your hidden state represents where you started and the less it knows what you wanted. Turns out that kind of thing still occurs. It just occurs at much greater scale. So if you ever ask it to give you a list of 52 items or write a 3,000-word essay, you'll notice that it caps out somewhere down the middle and decides it's done. In this case, it was done at 30. If you ask it to write a 2,000-word essay, probably after 600 words, it's had enough of you. And this is a really classic sign of something being AI. This is also why if you ever try to use code reasoning, by the way, on large chunks of code, then it loses context. It can't necessarily join between the function at the beginning and the end. But let's look at some other examples. And everyone knows and everyone loves fake news, right? So let's take this headline. This is something really trivial to check. You can see that Gary O'Neill is still the manager of Wolves. You can see that there are some more signs. For example, there's no name, there's no author here. And that's because nobody wants to put their name on something that they know is AI generated. This is unsurprising. You'll also typically see that there's very low engagement. People generally don't want to give their opinion on something that they know is false. And the headline itself is of a sensationalist nature. You want people to click your article. Truth is completely arbitrary and oftentimes just gets in the way. Although this particular article, crazily enough, came out in May, as you can see. And apparently this AI had very weird predictive powers because he was indeed fired on the 15th of December. So make of that what you will. So what are some other signs that we can look at? On the topic of sensationalism, right? This site is absolute gold. So you can see that the headline itself, a few hours ago, golf key player die in a brutal car accident. Ignoring the grammatical misgivings of this particular headline and the generic nature of it. Notice, by the way, here they even left in the beginning of the prompt, certainly, here's a detailed piece, blah, blah, blah. But indeed, looking at the site, moreover, you'll see that all the articles are of the same nature. This is a dead giveaway, right? These are the kind of things that give us confidence in our model. These were really simple examples. And here, let's look at some more interesting ones that I really like. Formatting is absolutely classic. You've probably seen that at times when you ask it to generate something, then you'll get these insert whatever information you need. A lot of people just leave that in. You have an automatic pipeline. People just don't notice it. This is really obvious, but this is a really interesting example. So think of a name, right? A name in the embedding space will have the exactly same vector. It doesn't matter if you're this James, that James, or the other James, right? You're still the same James as far as the vector is concerned. So here you have a really cool example of this. So you have Jennifer Jones, which is indeed a curling champion. Now, curiously, she does not have a daughter, and as a result of not having a daughter, it's very difficult for her daughter to die. Now, this is a case of mistaken identity. The Jennifer Jones they're actually talking about, who did have a daughter, is this one, an actress from 70s. This is something that happens a whole time. You can see that because of the nature of names, that you have cases of mistaken identity. It's a really cool thing that occurs specifically in LLMs. This isn't a mistake a human could reasonably make. Now, these examples aside, you can also ask yourself, okay, so how do they generate these articles? How do they come up with the headlines? So we saw the sensational site from before that I presume just has a list of type of brutal death and sport and combines those two, which is one way to go about it, I suppose. But another thing you can do is you can go to YouTube, right? Take a video, take the title of the video, spin that out into an article. How can you know that the article is in fact false? You find the video, you listen to the video, and I spent 14 minutes hearing about Justin Bieber and the FBI. I can assure you that two things. One, it had nothing to do with this article, and B, my brain cells died listening to this. It's not that interesting. The worst part was how many views this video had, but alas. And this is how you generate these texts. But why? Why do you do this, right? So you have the obvious cases. You want to make ad revenue, you want to destabilize governments, you want to create social disharmony. That's great, but everyone's been doing that. What else can you do? You can use it as a front for fraud. What do I mean? So here are two sites, and I'm going to show you the traffic patterns on them. So what you have on this x-axis, each row represents two different sites. You have the local hour time and the traffic by day. Now, both these sites, you can see they had a pulse of traffic on a specific day on content that's AI generated. Why do they do this? Simple. You want to sell ads, but you want your site to look legit, right? The traffic isn't real, but if somebody checks, having a blank page with 500 ads probably doesn't look that good. So you use the AI-generated text as a cover. You use it to give your web page a front of legitimacy. And this is just one of the more exotic uses that we saw. We also saw a bunch of groups on Facebook that simply infiltrate groups and spam it with all kinds of AI-generated content to links with yet more AI-generated content, et cetera, et cetera. Honestly, I'm impressed by the creativity that people have with how to use this AI-generated text. It's impressive. When fraud is concerned, people get really creative. And that's all I have to say. So thank you very much.